Hello, thank you for coming to this talk. I'm extremely glad that you're here. I'm very grateful to the organizers for organizing this workshop. I cannot imagine what it must be like to organize such a thing under the current circumstances, but I'm very grateful that they have done so. I feel a little uncomfortable not having anything to say either about Berkovich spaces or even about arithmetic D modules. And to be quite honest, the only thing tropical about this talk is the fact that here it is December, and yet I'm sitting on my front porch wearing a t-shirt giving a math lecture. So let us get started with it. So let's suppose that lambda is a complete regular local ring with fraction field capital K. The question is, can we expect that there is a quote-unquote reasonable cohomology theory, say h of x lambda, with its values in lambda modules, for separated schemes of finite type over a field little k? Of course, the answer to this question depends on what reasonable is supposed to mean. But for most definitions, the answer is yes, unless K and the residue field of lambda have the same positive characteristic. One of the basic requirements of reasonable should be that the Hn of x lambda should be finitely generated lambda modules. They should vanish for sufficiently large n. And I suppose also negative n's, although as long as they're bounded in some way. Okay, so this is the case, for example, when L is a prime, distinct from P, which is the characteristic of K, and the theory is p-adic cohomology, H of X, comma, CL. When L is P, in other words, when we are talking about p-adic cohomology, these requirements are met, provided that X is a proper K scheme, but not otherwise. But even in the proper case, p-adic cohomology does not satisfy a more stringent version of what reasonable should mean for a cohomology theory with lambda coefficients, lambda in this case being ZL, or ZP, I guess. Namely that if you extend the scalars up to K, the fraction field of lambda, the result should be rigid cohomology. Sorry, K should be the fraction field of the Witt vectors of little k. So if you extend scalars, you want to get rigid cohomology. That's certainly not the case for p-adic cohomology if X is proper. Or, I mean, this is not to say that these groups are totally without interest, either when X is proper or more generally, X separated of finite type over little k, and you're looking at the p-adic cohomology with compact supports. When K is perfect and X is a smooth K scheme, Davis, Langer, and Zink have defined an overconvergent version of the de Rham-Witt complex. And they've shown that if you take its, so this is a complex of WK modules, WK being the Witt vectors, and they showed that if you extend scalars, you tensor with Q, then the result is in fact isomorphic to rigid cohomology, at least when X is a quasi-projective K scheme. You might entertain the very faint hope that these are finitely generated WK modules. We will see actually that this is never true if X is a smooth affine curve. Davis, Langer, and Zink make the more reasonable conjecture that the image of the hypercohomology of overconvergent de Rham-Witt in rigid cohomology is finitely generated as a WK module. But Ertel and Shiho, unfortunately, have produced counterexamples to this assertion as well. In fact, curves. Yeah, so it's that bad. And you have to keep in mind the original motivation for crystalline cohomology, which was the study of p-torsion phenomena. So if you have some proposed cohomology theory that involves killing all p-torsion, this seriously reduces its interest. Okay. The folk wisdom is that there is no quote-unquote reasonable integral p-adic cohomology theory for separated schemes of finite type over field of positive characteristic, okay, where the the P here and the P there are the same. The theory I wish to explain today makes the prospect of this rather unlikely, though it doesn't completely exclude it. So, this is a joint work with Tomoyuki Abe, and I would like to thank him for many enjoyable conversations on these matters. So for the rest of this talk, lambda is just a complete local ring with residue field little k and fraction field capital K. As usual, d-perf of lambda is the triangulated category of perfect complexes of lambda modules. And since lambda is a local ring, this means that an object of d-perf of lambda is quasi-isomorphic to a bounded complex of free lambda modules. This simple observation will actually be used later. So the following requirements could be viewed as, or I shall choose to view them, as being reasonable requirements on a cohomology theory, h of x, say. First of all, you should be able to use them to compute rigid cohomology, or failing that, rigid cohomology with compact supports via a suitable comparison theorem. You should also be able to compute these groups as the cohomology, in the usual sense, of an object of d-perf of lambda, of a bounded complex of projective lambda modules. And finally, these groups should be compatible with finite étale descent, in a sense to be explained in a moment. Okay, so I mean, this you may feel is adding a little bit here, but you know, in fact, most known cohomology theories have this property, and you really want it to happen. When lambda is regular, the second requirement here just reduces to the condition that the Hn of x's are finitely generated lambda modules and vanish for sufficiently large n. To explain the last condition, I will use the finite étale site, whose definition we now recall. So X is a scheme. So then the finite étale site is the category of finite étale morphisms, y to x, and coverings are surjective morphisms. The associated topos will be written in the usual way. A morphism pi of schemes, okay, induces a morphism on the finite étale topi, and this, of course, gives you functors pi upper star and r pi lower star. There's also a projection, alpha, from the étale topos of x to the finite étale topos of x, and it's compatible in an obvious sense with the morphisms of the étale and finite étale topi. Okay, so I make the following definition. An object M of the derived category of lambda modules on the finite étale topos is globally perfect if, first of all, it has finite Tor dimension, and secondly, for every morphism pi from y to x in the finite étale site of x, the derived global sections on y of the pullback of M is in d-perf of lambda. To show you that such things really exist, we could consider the case where X is a smooth and proper K scheme. V is the Cohen ring of the base field little k. And now if O sub X over V is the structure sheaf of the crystalline étale topos of X, and if U is the usual projection of the crystalline étale topos to the ordinary étale topos, then if I push this thing all the way down to the finite étale topos, I get a globally perfect object. It's just the ordinary finiteness theorem for crystalline cohomology, just tarted up a bit. If X is a separated K scheme of finite type, you can also show that there's a globally perfect object M of the d-perf of ZP modules on the finite étale topos, such that H of pi upper star of M is I'm sorry, I should have had global sections in there. Yeah, this is just the ordinary p-adic cohomology with compact supports of y. This is for all morphisms pi from y to x in the finite Ital site. So let's suppose that h dot is a functor from the finite Ital site to the category of n-graded k modules, k vector spaces, okay? So you can take it, for example, to be the restriction to the finite Ital site of your favorite k-valued cohomology theory. Okay, so a globally perfect model of this functor is a globally perfect object M of d-perf of lambda modules on the finite Ital site of X, and a functorial isomorphism of H of Y with ordinary cohomology of the derived global sections over Y of the pullback of M, all of it tensored over lambda with its fraction field, capital K. This is for all morphisms Y to X in the finite Ital site of X. So it's a fairly strong kind of finiteness, but so, you know, the finite Ital topos is a very coarse kind of thing. So it's reasonably general here. The requirement that H have a globally perfect model is slightly stronger than what I earlier described as reasonable, since I'm now requiring that M have finite Tor dimension. However, if lambda is regular, this is not a serious issue. The key technical result behind everything is the following theorem. So let's suppose that lambda is Noetherian and X is affine. Okay. So if M is a globally perfect object on the derived category of lambdas on the finite Ital topos, and if Y is a finite Ital Galois cover of X, pi is the morphism from Y to X. If this is finite Ital and Galois with group G, then the derived global sections over Y of pi upper star of M is a perfect complex of lambda G modules. The sense of the latter assertion is simply that there is an object in d-perf of lambda G modules, okay, whose image in d-perf of lambda modules computes the derived global sections on Y of pi upper star of M together with the natural action of G on this object. Okay, I'll need some technical business about cohomological dimension here. So let's recall that if R is a ring and if X is a topos, then the R cohomological dimension of X is the smallest integer d, such that Hn of X comma F vanishes for all n greater than d and every R module F in the topos X. Okay. And then our lemma about cohomological dimension is as follows. Suppose K has positive characteristic P, and X is a K scheme of finite type. So then the Z cohomological dimension of the Ital topos is finite. And if X is affine, then the Z localized at P cohomological dimension of the finite Ital topos is also finite. I'll just sketch this since it's basically in the literature. The first assertion is actually a theorem of Gabor. You can find a proof, for example, in a recent paper of Sisinski and Diglies. For the second, I begin with the result of Abbas, Gros, and Tsuji, which asserts that when X is affine, then the finite Ital topos of X is equivalent to the classifying topos of the fundamental group of X. Therefore, it's enough to show that the group cohomology, Hn of pi1 of X with coefficients in F vanishes if n is sufficiently large, and this for all continuous pi1 of X modules F. Okay, well, back when I was a youngster, Sayre showed that Hn of pi1 of F is torsion for all positive values of n. So if f is a Q module, then these groups actually vanish, again, in positive dimension. And again, by Abe, Gros, and Tsuji, the finite étale topos is a coherent topos. Therefore, the classifying topos is as well. And what that means is that the group cohomology, Hn pi 1, commutes with inductive limits. And then you just use a simple dévissage using this utterly standard exact sequence. This reduces us to the case when f is a p-torsion module. But in this case, Achinger showed that there are actually isomorphisms of the étale cohomology of f with the group cohomology pi 1 with f. Okay. And then, so the assertion follows then from the étale case. So that's the proof there. Okay, in what follows, I will somewhat confusingly use the symbol lambda to denote the sheafification in the finite étale site of the constant pre-sheaf with value lambda. Okay. Okay, so next lemma. For any morphism pi from y to x in the finite étale site, and for any m in the bounded below derived category of, I guess I should say lambda modules, in on the finite étale topos, there's a functorial isomorphism of r pi lower star of r pi upper star of m with m tensor upper L over lambda with r pi lower star lambda. Okay. This is utterly unsurprising. I'm sure you will agree that this is obvious in the étale site, and it's just a matter of a few technicalities to get it all to work in the finite étale topos. So, okay, so first of all, we start with the adjunction pi upper star of r pi lower star lambda to lambda. We get morphisms of the pullback of m tensor upper L over lambda of r pi lower star of lambda. Okay, here lambda is sheaf on y. Okay, with the tensor upper L of the two pullbacks. Okay, but then the adjunction maps the second factor here, pi upper star of r pi lower star of lambda, to lambda itself. So the target of the adjunction, well, the target here then just melts down into pi upper star of m. Okay, so this is the morphism that is in the lemma. Okay. And to check that it's an isomorphism, it suffices to check after I pull back by a covering morphism, say g of w to x in the finite étale site. Okay, I claim that g upper star and r pi lower star commute. So here we use a result of Abbes, Gros, and Tsuji, who show that g upper star has an exact right adjoint. So this means that g upper star sends injectives to injectives, and that's all I need to prove this claim that they commute. So since g upper star and r pi lower star commute, I can replace the morphism pi by its base change by g. Okay. So then all I have to do is pick a finite étale g from w to x with the property that the pullback scheme w times y over x is a disjoint sum of copies of w. And in that case, you know exactly how the group acts, and the proof is easy. So that's it for the lemma. Okay, now I prove the theorem. What I have to show is that derived global sections over y of pi upper star of m, okay, is a perfect complex of lambda of g modules. And of course, it's isomorphic to r gamma derived global sections on x of r pi lower star of pi upper star of m. Okay, so we start looking at r pi lower star of pi upper star of lambda on x, which is the exact same thing as r pi lower star now of lambda on y. I'll denote this by calligraphic g. Okay, and okay, well, this naturally has a g module structure, and in fact, it's a flat g module. Yeah, it's a flat. Sorry, it's a flat module over the group ring lambda of g. group ring on X, of course. It's actually flat by the argument of the previous lemma. Okay. On the other hand, that lemma also gave us an isomorphism of our pi lower star with pi upper star of M with M tensored with this thing G. Okay, so since G is a flat lambda of G module on X, and M has finite Tor dimension, and I'm sorry, this should be a finite Tor dimension of X comma lambda, X finite tau topos. Okay, so that shows that R pi lower star of pi upper star of M is actually, again, on the finite tau topos, it actually has finite Tor dimension as a complex of lambda G modules, okay, where the lambda G structure comes from this isomorphism, okay? And then if I take derived global sections, then I wind up now absolutely with a complex of lambda G modules with finite Tor dimension. Okay, well, X by assumption was affine, so the lemma on cohomological dimension then says that our gamma on the finite tau topos of Y of pi upper star of M, which is isomorphic to our gamma of X finite tau R pi lower star, pi upper star M, actually lies in the bounded derived category of lambda G modules. On the other hand, by assumption, right, that this is globally perfect, these are also finitely generated, the HNs are finitely generated lambda modules. They are, therefore, finitely generated lambda G modules. Okay? And since lambda is Noetherian, that means that our gamma over the finite tau topos of pi upper star of M, this is actually a perfect complex of lambda G modules. Now we get to the main theorem. Little k is our base field. I will denote by k naught the fraction field of a Cohen ring of little k. And recall that capital K is the fraction field of lambda. Okay, I can make it into an extension field of k naught. And in what follows, rigid cohomology is going to be taken with coefficients in k naught. Theorem says the following. Suppose K is now a field of characteristic P, positive. X is a smooth affine curve over little k. And lambda is a complete Noetherian local ring with residue field little k and fraction field capital K. So then the functors from the finite tau side of X to graded K vector spaces, which are either rigid cohomology, tensored up to capital K, or rigid cohomology with compact supports, again, tensored up to K. These two functors, neither of these two functors has a globally perfect model. Okay, so proof is actually not so hard. A smooth affine curve X has an Artin-Schreier cover, pi from Y to X, that ramifies at infinity. I leave this as an exercise for your students. So it suffices then to prove the following lemma. So let's suppose that X is a smooth affine curve over field K of positive characteristic P. Sorry. Pi, a morphism from Y to X, is a finite Ital-Galois cover whose group G is a P group. And M is a globally perfect model of either of the functors that we are talking about, either rigid cohomology with its scalars extended to K, or rigid cohomology with compact support, again, with scalars extended to K, okay? Both from the finite Ital site of X to the category of M-graded K vector spaces. Okay, so if this globally perfect model in either case exists, then the morphism pi from Y to X extends to a finite Ital morphism pi bar from Y bar to X bar of smooth projective curves. In other words, this map pi, it's unramified everywhere. Okay, so as usual, I will denote by chi of Z the rigid Euler characteristic of a separated K-scheme Z of finite type. if Z happens to be smooth, then chi of Z is also the alternating sum of the k-naught dimensions of the cohomology groups, rigid cohomology groups with compact support. That's just duality. So in this case, the third hypothesis of the lemma says that I can compute the Euler characteristic of Y for any Y going to X in the finite Ital site. Its Euler characteristic can be computed as the alternating sum of the k dimensions of this theory. Okay, and yeah, but by this I mean you extend scalars to k. Sorry, should have done that. Okay, well, again, by assumption, this isomorphism is supposed to be functorial. Okay, so G, which acts on Y, acts on this as well, and by the previous theorem, there is a perfect complex, let us call it M sub Y, of lambda G modules, such that Hn of My tensored with K is isomorphic to the rigid cohomology of Y with compact supports, again, tensored with K. And if I take G invariance, then the, again, if I'm, yeah, I've tensored with, I'm sorry, I should have tensored with K over here, so tensoring, so G invariance is exact. And I will get now the rigid cohomology with compact supports of X, again, with its scalars extended up to K. This is because pi is a finite Ital morphism from Y to X. And now here's the key trick. G is a P group. So the group ring lambda of G is local. There's a local ring. Okay. So a finitely generated projective lambda G module is actually free. So in other words, this complex lambda Y that's computing the cohomology of Y, it's a bounded complex of free lambda G modules. And what this tells us then is that the Euler characteristic of X is order of G times the Euler characteristic of Y. And this is just so wrong. If you compare this with the Grothendieck-Ogg-Shafarevich formula, this can only hold if the ramification of pi is tame at infinity. Okay, but this is, I mean, this is, but you know, G is a P group, so if pi ramifies at all, it has to be totally wild at the ramification points, which are therefore ad infinity at the points of the completion Y bar that are not in Y. Okay, so what this means, of course, is that pi is unramified at infinity, and that is the conclusion of the lemma. Okay, so that's that. Let's go back to Davis, Longer, and Sink. So let's suppose K is perfect, and I will take the functors to be the functor to be is the nth hypercohomology of overconvergent de Rham Witt on X. As always, W is Witt vectors of little k. And one can show that if, in fact, these things are finitely generated W modules for X, actually, I just need for all morphisms in the finite Ital site and all non-negative n, then this complex here would be a globally perfect model of the rigid cohomology. Sorry, at least if I, no, yeah, it would be a globally perfect model of rigid cohomology. Okay, which is, but the theorem says that this is false for every smooth affine curve X. And in fact, Ertel and Chiho have constructed smooth affine curves for which even the H1 of this thing is not finitely generated modulo torsion. So, okay, well, I've actually come to the end of my lecture, so you'll get out early today. Thank you very much.